this statue had to be renovated in the 1980s. So this statue, the copper part of it was made by a French sculptor, but if you could take off all that copper sheathing, you'd see something that looks a lot like the Eiffel Tower. And that's because the structure underneath was designed by Gustave Eiffel. And so it's an iron structure just like the Eiffel Tower. And if we had not renovated it, it would have started falling apart. So let's look at why that's so. So I'm just going to make a quick sketch here of the inside of the Statue of Liberty, and it's going to be a little oversimplified. So imagine that we have, let me get a color that will show up here. There we go. Okay, so imagine that we have the statue, which I'll just show as a series of arches. So it's going to look like the Eiffel Tower. That's actually what it looks like underneath. So all this is made of predominantly iron. And then on top of that, we have this copper structure, which you could show as green if it's started to corrode a little bit, or red if it's brand new copper. Now, remember, of course, the Statue of Liberty is in the harbor of New York, and so it's exposed to salt water, just like any structure here on the West Coast is exposed to. So I'm going to zoom in on this, and let's just look at the junction between the iron and the copper. So we'll use, I guess I don't want to use black. I'll just go ahead and use gray ink for everything and just label it. Yeah, I think if I use black, that would be a bad idea since the background is black. Okay, so we've got this skin that's iron. And then on top of it, we have copper. Okay, so we've got copper and iron. And originally, they were not touching. So Gustave Eiffel did understand chemistry, and so there was actually between the outer skin of copper, and there's actually some sort of saddles on the copper that are also made of copper, basically straps, and there were connectors that were made of iron. But basically, eventually, you had to connect somehow the copper to the iron. And what Gustave Eiffel did was coat those connectors in a cloth wrapped. It was an asbestos cloth covered in shellac. And so it's basically like a primitive form of a composite that doesn't conduct electricity. And that's great. And for a while, it worked. But then it corroded, it basically fell apart. And we ended up with the copper would eventually come in contact with the iron. So we had direct copper to iron contact. And as soon as you have that, what do you have? You have two metals with different reduction potentials in contact. And when they're in contact, they can transfer electrons. So if one of them gets oxidized, the other one can act as this giant cathode that can basically carry the electrons to whatever the oxidizing agent is. And that's exactly what happened. So what happened is, if you look at reduction potentials, I'm just going to flip down here for a second to reduction potentials. The more positive the reduction potential, the more easily corroded the metal is. And so if we look at copper, okay, so copper is down here, it is positive, so it's easily reduced. And if we have a negative reduction potential, we're more easily oxidized. So we look at iron, okay, if we go to iron 2, for instance, it's got a negative reduction potential, it's easily oxidized. So we have a metal that's easily oxidized and a metal that's kind of hard to oxidize, and it's actually easy to reduce. So whenever you put two metals like that in contact, one of them is going to corrode at the expense of the other. And so let's look at what that looks like in terms of a cell. So we're going to draw a corrosion cell here. So remember that this whole thing is in contact with salt water, because whenever the waves create aerosols that are basically droplets of water filled with sodium chloride and other salts, and those get blown in, and even sea fog has a little bit of salt in it from the salt air. So what we've got here is this film of water on top of the copper, and it's got sodium ions and it's got chloride ions in it. So not only does it have ions in it, it can conduct electricity, and that's when those ions move, it's basically conducting electricity. And the problem is there are holes, these rivet holes, that allowed water to get in. So eventually we ended up having water down here too. So we have sodium ions and we have chloride ions down here. And now these metals are in contact. So what can happen? Iron can start to, I'll put another film of water out here. So we've got water, and we've got sodium ions, and we've got chloride ions. So iron can corrode to start forming iron plus 2. Now, if it did that, we know what happened. It lost 2 electrons. So where do those electrons go? If those electrons piled up here, it would be hard for this iron to get oxidized because it's leaving behind a negatively charged object. This is going to get negatively charged if the electrons pile up. But what if they don't have to pile up? What if those electrons have an escape route and they can come up to the copper over here? Well, can we come up with an electron acceptor? An electron acceptor, another word for that, is an oxidizing agent. So we've got oxygen here, and we can end up with that oxygen pairing up with electrons. They're flowing up from the copper, and we end up forming hydroxide ions. So notice what we did. We reduced our oxygen, we oxidized our iron. Okay, and the rate at which this happens is going to be limited by surface area because it's at the surface where the copper is giving those electrons to the oxygen. Let's look over here for a second at the Statue of Liberty. That copper sheathing is a giant cathode. It's all this surface area that's covered with a film of water from sea fog. And so it's a wonderful cathode. And so what this means is this iron has a giant sink for sending its electrons to get paired up with oxygen to make hydroxide. So it really accelerates the corrosion of the iron to be in contact with the copper. So this is called bimetallic corrosion, or it's also called galvanic corrosion because you're basically making a giant galvanic cell. So again, a galvanic cell is just another name for a voltaic cell. So it's a cell where the delta G standard is positive. Or another way of saying this is that the delta G standard is negative and the E standard is positive. So if we write this, we've got delta G standard is negative, so we've got a K for this reaction, which is going to be greater than 1. We can also say the E standard is going to be a positive number. Okay, so all of these are basically synonyms. Okay, they're product favored reactions. So this is just one more way of doing this. So just let me remind you that we have an equation that relates these things, which is E standard is equal to negative. Oops, I got this backwards. Let me erase that. Delta G standard is equal to negative NF E standard. And okay, so what that tells us is obviously if we have a favorable reaction, it's negative delta G. Favorable being you have a lot of products at equilibrium, it's a negative delta G standard, and it is a positive E standard because that negative sign. Okay, so this is how this corrosion works. So I want to draw this cell again a couple of different ways just to show you what it looks like. Okay, all right, so I'm going to go on to the next page and we're going to examine this, show us how this would look if we didn't separate it with a wire and what it looks like when we separate with a wire, and then we're going to label all the components. Okay, so we could imagine, if you think about that reaction, what are we doing? The net effect, go back to it for a second. Notice the copper is not actually taking part in a reaction. The copper is just a place where the reaction can take place, where one of the half reactions can take place. We call that an inert electrode. Okay, so let's look what that looks like on the next page. So we could imagine, if we look at this reaction, what are we doing? We're taking iron, we're taking oxygen, and we reduce the oxygen to hydroxide. Okay, the hydrogen just comes from water. And so we went from, actually we'll do the oxidation numbers because that was one of the other questions. Went to iron 2. So we could actually do this directly. We could actually just take oxygen and put it in contact with water and iron and do this directly. We don't have to separate out by a wire, but I'll show you what it does if we do separate it out by a wire. Okay, looking at this, we claim that this is, and we'll just make a note that we haven't bothered to balance it here. Okay, we claim this is a redox reaction, that the iron got oxidized and the oxygen got reduced. Let's double check. So this is an element, so we know it's 0. We come over here. This was, oops, we made iron +2 aqueous. So if it's just a monoatomic ion, it's just the same. The oxidation state is just the same as the charge. So that one's easy. And over here, elemental state, oxygen 0. Come over here. Oxygen in any compound other than a peroxide is going to be -2 in compounds. Okay, so notice that we reduced the charge. We went from a more positive number to a more negative number for the oxygen, and we increased our oxidation number on our iron, so that's oxidized. Okay, so we got oxidized, and we got reduced. Okay, so clearly that part makes sense. So we could do this directly, right? We could imagine just combining these things in one beaker. Okay, so indeed we could, if we wanted to, and actually you did this in your experiment. You can imagine taking a beaker of water, and you've got oxygen, which can dissolve in the water, and you could have a piece of iron in there, and if it's close enough to the surface that it has access to oxygen, it can rust, right? We can start forming iron 2, and we start forming hydroxide. And those can combine to form iron oxide. So if it accumulates on the surface, the hydrated iron oxide is what, or hydrated iron hydroxide is what we call rust. This does require oxygen, by the way. So if you go to the very bottom of the ocean where the water is not very well oxygenated, you tend to get less corrosion. So it takes a long time for things to corrode at the bottom of the ocean because the oxygen, there's so little oxygen in the water. But surface waters, if you're right below the surface, or better yet, something like a piece of a dock where you're sprayed with water, but then you're exposed to oxygen constantly, then you corrode really fast. So this is all in one beaker, but we could just as well have done this in 2 beakers, couldn't we? Let's do this in 2 beakers. I'm going to go ahead and move to the next slide, just so that I can draw it a little more clearly. So we're going to draw this as a classic cell with 2 beakers. And I'm going to say I'm going to have oxygen coming in here. I'm going to need a wire connecting these, so I'll just call this wire here. And I'm going to have, let's have this piece be a piece of iron. Okay, now we can imagine, let's put this, we're going to have some electrolyte in both of these. Okay, so let's imagine that this iron is starting to corrode, and we'll even draw the corrosion on here. It's getting eaten up here. There, that's a little more dramatic. Okay, so now ions are going out into solution. Well, if they're going out into solution, what's happening? They're leaving electrons behind. And if those electrons were to pile up, we'd have this giant negative charge here. It's not energetically favorable because they repel each other. So what do? The electrons go through the wire. Okay. And if those electrons go through the wire, they're going to come over here. They're going to pile up on that wire unless we have some way of getting rid of them. Well, remember, we could use oxygen as an oxidizing agent, something that gets reduced, that acts as an electron sink. If we do that, we need a reaction. Well, we have a reaction. We have this oxygen can come down here, react, take electrons off, from this thing. That's a horrible picture. Let me see if I can draw a better one. So we have an electrode here, and electrons are going to go out to the surface, where they're going to react with the oxygen, and off comes a hydroxide because we reduced the oxygen from 0 to -2. Of course, we also have water reacting in here to give us our hydrogen. Okay, so electrons come off of this electrode, and they are dumped onto this electrode. So let's start labeling this, because one of the things we're going to do next week, because we're going to spend a whole nother week on electrochemical cells, is labeling components. Okay, and I'm going to pause here while you keep up with me. I'm just going to let's see. I want to make sure it says that it's recording. Okay, I'm a little nervous that it's not saying it's recording, so I'm going to open up a second piece of software to record as kind of a backup, just so that we have something if Zoom doesn't work, since I'm unfamiliar with the new software. Okay, so new recording. Okay, good, start recording. Okay, so I have a backup recording in case Zoom doesn't work. Okay, so looking at this, we've got oxygen coming in and being reduced. So we can label this as the cathode. And we've got our anode over here. Now, an important point, and this is a question that I got in the, I got a question about this in the forum, which was, how do I know if one of my electrodes is inert? When an inert electrode is something that doesn't take part in the reaction. And an important note here is that electrodes are just conductive things, conductive surfaces where electrons are taken from something or given to something. So electrodes are locations. They're the surface of electrodes. So the cathode is the surface of an electrode, and the anode is the surface of an electrode. So it turns out that if we look at this iron over here, that this electrode is actually a reactant, right? The iron is being oxidized, and it's also the electrode. But if we come over here, what's reacting? Oxygen. It's picking up electrons. Does it care what it picks it up from? No. This electrode could be anything that conducts electricity. So it could be platinum, it could be gold, it could be graphite. Anything that conducts electricity would work. Okay, so that's an example of an inert electrode. So if the reactant is coming in from the solution and going back out into the solution, then the electrode is just a way to transfer electrons. Okay, so this is an example of an inert electrode, this cathode over here. So it's always true, no matter what kind of cell you have, that reduction occurs at the cathode and oxidation occurs at the anode. Okay, let's see if there's anything else we can do. Oh, so if you're familiar with circuits, you might recognize that our drawing is not complete. We have a circuit. If we look at the flow of electrons, we have, let me see if I can find a little spotlight here. No, I don't have one. I'm just going to use my pen as I'll use the cursor here. Okay, if we look, the electrons start at this electrode. They're flowing over here. They're coming over here. That means we have negative current, negative charge flowing anti-clockwise. Wait a minute. It can't just stop. We can't have a circuit that's not a loop. A circuit needs to make a loop. So we have to somehow complete this circuit. And another way of looking at this problem is you're creating all these negative ions over here. Well, you can't have just negative ions in a solution. You've got to have counter ions. So somehow we need more positive charge to pair up with that. I don't mean pair up in the sense of it's not going to necessarily join up to form a compound or a precipitate. I just mean to maintain electron neutrality. We need something positive since we've got something negative. And over here, we're generating cations, so we need some anions over here. Both of those things, electron neutrality and completing the circuit are filled with a salt bridge. And I think I mentioned this, well, actually I know I mentioned this in one of my other videos. A salt bridge is usually made just by making some salty jello. And so you could literally use jello, or we tend to use agar, which is basically sort of like vegan jello. It's made from, it's the gooey stuff from seaweed. Okay, so you can dry it out and then reconstitute it. And so it's a nice way to make a gel. So you've got a gel, and inside that gel, you've got some potassium ions and some chloride ions. You could use other salts. Those are just the ones that are really common. Okay, so you have this potassium chloride salt in here. And the reason we use that is beyond the scope of the class, but basically the mobility of those two ions are very similar. Okay, so what happens is we were building up a positive charge because of this, these cations being formed. So the chloride ions will migrate this way. And we need to have a cation to pair up with this in terms of electron neutrality, so the potassium ions go this way. So notice what happens. We have a net flow of negative charge in this anti-clockwise direction, right? So in the wire, the charge is in the form of electrons. Okay, so through conductors, like any kind of metal, the almost exclusive charge carrier is electrons, right? They're really mobile, and then everything else is hardly mobile at all. So basically just electrons moving through here. And then in solution, the primary charge carrier is going to be ions. And so notice the chloride ions are moving this way through the salt bridge, right, to complete the circuit. So we have negative charge moving in this direction, and the positive charge is moving in the opposite. Okay, so we have a complete loop. All right. All right, so notice this is the same thing as having oxygen and iron react in the same beaker. The only difference is that we don't have to. As long as we can complete the circuit and we can have the electrons flow by connecting a wire, we can separate the cathode and the anode in space. They don't have to be touching, they just have to be connected by something that can carry electrons. Okay, so with that in mind, I want us to redraw the Statue of Liberty in terms of a beaker. Okay, so we're going to redraw the Statue of Liberty. So a different, actually, all we have to do to make this a Statue of Liberty is to make this copper. I don't have to make all in the drawing. So copper has a very positive reduction potential, so it tends to stay in its reduced form. And so it acts as inert electrode. So that whole surface of the Statue of Liberty was acting as an inert electrode, and its only role was to deliver electrons to oxygen. Okay, the salt bridge in this picture, so in this picture that separated into two beakers, in the Statue of Liberty, the salt bridge in the middle here was just the salty water that was between the puddle of salt water between the structure of iron and the skin of copper. And then any place the two metals touched, that played the role of the wire. Okay, so that's our first example of, or an example of bimetallic corrosion. Okay, I'm going to move on to the next question, which was, how does this relate to the reaction, the lab questions? And so what I'm going to say here is nothing new. It's something you already know, but I want to sort of point it out and highlight it. And that's, in the lab that you did, you had two indicators. So normally the corrosion, until it really builds up, is going to be invisible. And so we had two indicators. We had blue and pink. And they both signal something. They're both just indicators for specific species. So the pink is phenolphthalein. It's just an acid-base indicator that shows you have a lot of hydroxide. And blue is, well, it's Prussian blue, but it's a complex that is formed when you had the precursor for it in your gel, and then if iron 2 formed, it reacted with that precursor to form Prussian blue. So that's all these things mean. So I often have students in office hours, and they'll say pink means reduction and blue means oxidation. Well, sort of, but not exactly. Blue just means iron 2 is present. You produced iron 2. And pink just means you produced hydroxide. And the main way you would make, or actually the only way you'd make hydroxide in this experiment, is if you had oxygen gaining some electrons. So you've got water coming in, and you've got electrons coming in. You can make hydroxide. So indeed, pink means that oxygen was reduced. But notice if something else is reduced, you wouldn't see pink. So pink means specifically that oxygen's reduced. And the same thing with the blue. The blue, you didn't have any iron in your solution. You didn't have any iron 2 in your solution when you started. You had iron in the form of your nail. And so if your iron loses electrons, you're going to form iron 2. So if iron is oxidized, you're going to have blue. But notice if something else is oxidized, you won't get blue. Okay, so it's not as simple as saying blue means oxidation. Blue means specifically that iron was oxidized. Okay, so solving these nail photos is kind of like, it's a puzzle. And the key pieces of the puzzle are electrons don't swim. They go through metal. They flow through metal. Ions do swim, right? They go through solutions, or a gel is just a network of solid that's interpenetrated by liquid. So a gel is just like a sponge. So if you think about anything that can diffuse through water can diffuse through a sponge. And so your gel is just like a very, very wet sponge. And so your ions, any kind of cation or anion can diffuse through the gel. And the last piece of the puzzle is that you can't have reduction without oxidation. They always have to be paired. So if one is happening, the other is happening. Okay. All right. I think that answers a lot of what I had on the, I'm going to look at my notes here for a second. There was something else I wanted to talk to you about. Charge. I want to do charge. That's one last thing before we move on to the next topic. Okay. So the question I'm going to ask is, and I'll have you vote on this. So get ready to vote yes or no. Let's see. Yes. Okay, so here's the question. Is the anode positive? So, and I want you can sort of memorize this, and students do, that's okay, but you don't have to memorize this. You can logic this out. So is the anode positive? Okay, so if I were to put my lead on iron and the other lead on copper, would it say that iron is got a positive potential with respect to the copper electrode, or a negative potential? So is anode positive? So I'd like you to vote now using the yes or no. So answer that yes or no. So I'll give you a second to think about it and then vote. Okay, I'm going to look at your votes. Let me clear your votes and have you revote. Okay, go ahead and vote now. Is the anode positive? Okay. Okay, so I'll tell you what the, interesting. Okay, so the majority vote looks to be Yes. Let's figure out if that makes sense. Okay, so the anode is where oxidation is taking place. And we have iron being oxidized, leaving behind its electrons. Okay, so electrons are going to end up initially being piled on this electrode. Okay, so let's vote on that again. So is the anode positive? Okay, wow, that looks like it's, you guys are still voting, but it looks like it's going to end up being unanimous as a no. Okay, no. So the anode is going to have a negative charge on it, a negative potential. And that makes sense because what happens, you build up this negative potential and that's going to repel electrons to the electrode that's more positive. Let's put a little positive on here. And if we think so, electrons are going to be repelled by this negative charge, they're attracted by this positive charge, so they flow through this wire. And so you can think of it as what's going to happen here, you're pulling, the oxygen is pulling electrons off that cathode. If it's pulling electrons off, that's going to leave an excess of positive charge. Okay, so this is not going to apply to some of the things we do next week when we do electrolytic cells, but right now we're talking about voltaic cells. And the phrase I want you to remember is, in a voltaic cell, the chemistry is in charge. You've got a reaction with a negative delta G standard. So that reaction has a strong tendency to go forward, and so it's going to force electrons, it's going to push them around. So in the case of the anode, the iron is getting oxidized and it's just dumping its electrons on that anode. In the case of the oxygen's over at the cathode, ripping electrons off that cathode. And so it's forcing the flow of electrons. Okay, so that's what's going on with voltaic cells, is the chemistry is in charge and the electrons get pushed around. Okay? Okay, so I'll underline this and we'll do these. So one of the questions that you might get asked in a checkpoint in either this week or next week, well, definitely next week, and perhaps on a quiz, is being able to annotate a cell, being able to build a cell and say, what's the cathode, what's the anode, what's the charge, the potential on the anode, what's the potential on the cathode, and showing where the ions are flowing and which direction the electrons are flowing. Okay, so I want to pause here and ask what your questions are about annotating a cell. And go ahead and, if you hit the chat button and then type into the, you can either send it directly to me or to the whole class. Oh, sorry. Okay, yeah, actually you can chat with anyone. You can chat with each other privately or me or the class or whatever. So if you type into the chat window, so if you have a question, I can just ask you that. Let me ask you that again. So if you have questions, say yes. If you don't have questions, say no. And if it's no, then we'll go on. Okay, so we've got, the question is, how do we know where the ions go from the salt bridge? And for that, the key is, I'm going to give you two different ways to do it. So one way is to look at the ions that you're generating in the reaction and saying, okay, I'm generating cations. I have to somehow balance those with anions. And that's how I knew to bring that chloride down. Or over here, I'm generating anions, so I need to balance those with cations, so I bring this down. Now, as for what ions are in the salt bridge, that would have to be given. Okay, so actually, I don't remember what you put in your agar. It might have been potassium chloride, it might have been sodium chloride, but that's not something you know. That would have to be given. If you're doing corrosion in the real world, in a marine environment, then there's all sorts of ions in seawater, but it's mainly is sodium chloride. I'm going to see if there's other questions. Cool. All right. Let's move on to oxidation numbers, because I did get a question about that. So I'm going to do one that's not carbon, because I did carbon in the lecture, and so I want to do a new one. Okay, so let's look at this compound. And we're going to do this two ways. Okay, so or this ion. So we know this is a sulfate ion. So what you have to do is look at the, you start off with looking at the ones you know. So we're trying to find the sulfur. The sulfur is the unknown. What's the oxidation number? And you see that this whole species totals out at -2. So we know whatever we total out, it has to end up being -2. So we've got something equals -2. We've got X for sulfur, and it's just one atom. So just one sulfur. And then we've got 4 oxygens. And this is a sulfate ion. There's peroxide is not in the name. So we know that oxygen in compounds are going to be -1, or sorry, -2. It's not a peroxide. So we've got X -8 is equal to -2. So we can solve for X by adding 8 to both sides. So we've got 8 minus 2 is 6. That's the algorithm method, right? That's just using math. Let's use the other method. So we're going to draw the sulfate ion. Okay, I put some formal charges on my oxygens there. Okay, now we're trying to find the oxidation number on the sulfur. So we look at all these bonds and say which is more electronegative, oxygen or sulfur. And fortunately, we have a periodic table handy. And we come over here, we've got sulfur and oxygen. So we can say, okay, we know that your oxygen has a higher electronegativity because it has a higher ionization energy and a higher electron affinity, because those electrons in the outer shell are closer, excuse me, closer to the nucleus, so they're harder to pull off. So we go back to our problem, we know that oxygen's more electronegative. So each of these bonds has a little bond dipole on it. So we do this for each of the bonds. And then we just circle what is on the sulfur. So if we look at this, there's 1, 2, 3, 4, 5, 6. So the sulfur is +6. And notice that's the same as we get with the algorithm method. And so having two methods in your pocket is really powerful, because it enables you to check your work. So you want to be able to do it 2 different ways, make sure they come out the same, and then you can be confident that you did it right. Okay, there's one last thing I wanted to talk about. Let's see, is the cathode always positive? I'm going to go back here for a second. For voltaic cells, the cathode is always going to be, the cathode is always where reduction takes place. And for a voltaic cell, it's the chemistry ripping electrons off, leaving behind a positive charge. So the cathode will always be positive in voltaic cells, yes. So one last thing, because we're going to run out of time, I think they set the Zoom for 50 minutes, is I want to make sense of these reduction potentials for a second. Why is it? So sodium has a very negative electron potential. It's very hard to reduce sodium, okay? Whereas we look at, if we, I think I can scroll down a bit. If we look at oxygen, it's really easy to reduce it. Okay, so why is it easy to put electrons on oxygen and it's harder with sodium? Well, the answer is right there in the periodic table. So we can build on the stuff from last quarter, and you want to tie in our new stuff to our old stuff. So we're going to look at oxygen, and we were comparing it to sodium. And there's our periodic trend. Remember, our ionization energy and electron affinity are both high for oxygen, right? It's favorable to add electrons to oxygen, and it's hard to take them off, which means oxygen is going to be easy to reduce and basically impossible to oxidize from its element. Like oxygen plus is not something we're going to have. Whereas sodium is over here. So it's easier to take an electron from sodium, and it really is bad at accepting electrons, okay? So since this is easier to take electrons from, it's going to have a more negative reduction potential. So even though you have tables, you can tie this into periodic trends from your previous course to make sense of the table. So try to do that, try to draw connections. One final question, and I didn't have time to fit this in, and then I realized I'd left it out, was how to calculate the number of electrons transferred when something reacts. So we'll just say number of electrons. So let's imagine that we have iron, or we could use oxygen. Let's say that we've got 64 grams of O2, and we're going to reduce that to hydroxide. So this reaction's not balanced, but we don't need to worry about balancing to figure out how many electrons were transferred. The way we do this is to use oxidation numbers. So we look at this, we said we went from oxygen 0 to oxygen -2. So that's 2 electrons transferred per oxygen. So if we look at for each of these, for each oxygen molecule, we're going to transfer 4 electrons to do this. So let's at least balance the oxygen. Let's put a 2 here. So 2 electrons per atom times 2. So we've got 4 electrons per O2. And that's the, oh dear. And that's the conversion factor we're going to need. So if we wanted to know the number of electrons, we would take what we know, which is 64 grams of O2. Like any other stoichiometry problem, we want to get rid of grams and go to moles. So there's 32 grams of O2 for every 1 mole of O2. So we cancel that. And we want to go to moles of electrons. And that's where this conversion factor comes in, right? If we have 1 mole of O2, we're going to have 4 moles of electrons. So we've got moles of electrons. The question didn't ask moles of electrons. You might have a question that asks the number of electrons. And whenever we want to go from moles to numbers, we just need Avogadro's number. Right? So we have 6.02 times 10 to the 23rd things for every 1 mole. So in this case, the things are moles of electrons. So moles of electrons cancels, and we get a number, a pure number. Okay, so we end up with 4.8 times 10 to the 24th electrons. So because a mole is such a big number, if we react to really not that big an amount of substance, we end up transferring a huge number of electrons.